Again, welcome to Lab 5, actually Lab 4 on week 5. We did Lab 5 on week 4, and now we're doing Lab 5 on Lab 4 on week 5. I know it's kind of hard to keep track of. I could have changed the labels, but I wanted to keep intact with the way that we had them on the syllabus. We listed Lab 4 as being basically the one that has to do with the momentum, and Lab 5 as the one having to do with the projectile motion. So I reversed the order a little bit because the momentum, we did it a long time ago, so I thought we should do the momentum first, namely Lab 5, and then we go and do Lab 4, which is really the projectile motion. But if in case it happens again in the future, I will probably keep you also posted. But that's the only change we are going through in terms of the syllabus, is the order at which Lab 5 and 4 basically happen, that's all. Okay, everything else should stay intact in terms of the order and the content and everything else. So if there's a change, you will know about it. So we're really in good shape, I think, to finishing all of the labs, the 13 or so labs that we're supposed to have in this class. So we're almost midway there, which is good. So we should be able to at least get 10 labs to call it really content that is that can classify as a content relevant for a course like this one. So we're in good shape to do that and surpass it actually and meet the entire 100%, basically all of the content we're supposed to do. Okay. Any questions about the lab that is due tomorrow? Remember, we changed the date when the labs are due now. Instead of being due on the same day when we're supposed to be doing the next lab, in order to allow everybody to be on board and come to the lab and not worry about the last minute calculations or finishing touches, and do them the day after, basically, to submit them Friday. So hopefully you guys have no problem with the lab that you should be done with. And if you do, please let me know. We still have another day basically to submit that. Okay. Yes or no? For those who submitted it, they submitted it, they're done. But they can go back actually and fix things. So as a matter of fact, I had a discussion with one of you guys on Monday, and I posted it, and I again announced the fact that it was posted. It was only a 13-minute basically discussion we had. So I wanted everybody to take advantage of that discussion, to, if they did not submit their labs yet, to make sure that they go through it and clarify anything that they're still vague about. Okay. So that's in terms of lab 5 of week 4. Okay. So today's lab, let me share with you let me first of all open the correct page. I don't want it to go into the wrong page in here. Let me go into the course Physics 11. And let's go to the modules. And let's open lab 4. And let me come back to Zoom now and share lab 4 with you guys. Okay. So this is, again, typical instructions that we're familiar with now, more or less. Hopefully by now you know exactly what you're doing in terms of when you come to Canvas, where to go and what to do. So you download the lab instructions, and from there you start working on your lab. Some questions that need to be answered, we're going to answer them together. The grading is here. Again, you have the entire rubric. This lab is graded out of 82 points. Okay. Questions all the time are worth 2 points. Sometimes you can get only 1 point out of the question. Objectives are worth 3 points. Sometimes you end up with only 1 point or no points at all, depending on how you go about it. Your name and that of the people who work with you. Conclusions are always worth 5 points, and they have a specific structure for that to receive the 5 points. Sometimes you end up with 2 points or no points at all, depending on how you did in there. Tables, they're worth basically, depending on the number of cells, they could be worth whatever the number of cells that you have in there. And the single entry data, for example, something specific, that's going to be just 1 point. So that's typical of how this thing has been running now from the beginning. We've been consistent with it. Everything is graded up to the last, basically, lab that was submitted. So the last lab that was basically that needs to be graded was submitted last week. So that's going to be graded this weekend, and so on and so forth. So basically that's in terms of participation, in terms of everything else. So that's typical stuff. So this is the lab report form, and I have it open. So I'm going to stop sharing the screen. Hopefully you guys come in here again and use your rubric as a guide to make sure that everything is done before submitting it. It's a good idea to do check mark. Did I do this? Did I do that? Did I do this? Did I everything in there? Once you have it all checked and you have finished it, then you can submit it. Don't submit something without probably the third question, I don't know, 7 or question 18, for example, for later. If you didn't do it, don't check mark it that you did it. So always have a check mark list with you to make sure that you're ready, or at least scan through it, make sure you do. Don't forget this multiple step back and forth to make sure that what you have uploaded is exactly what you wanted to upload, okay? So let's stop this sharing in here, and let's get into the actual lab report form itself, which is in here. And let me come back again and share that screen. Again, the introduction, hopefully you guys will have time to go through it and read it at least once to know exactly what we're doing. I know we did this in the lecture for Physics 10. I know those who took Physics 10 already know this stuff. The momentum is velocity times mass, and there is a need for it. This is in general because it's really a vector. The change in momentum is really the second law of the rate of change of momentum is the net force. That is actually the second law of Newton, reformulated in the case where the mass has the possibility of changing with time, or changing at all. I'm sorry, it doesn't have to be time. Mass is not fixed. And that's the impulse momentum theorem. And basically the energy, it's the sum of the potential plus kinetic in general. All collisions that not where only internal forces are involved, momentum is conserved. So the initial momentum must be equal to the final momentum. So if in case I'm dealing with a collision and I end up with the initial momentum not equal to the final momentum, I have a problem somewhere in there. I have an external force if I'm careful enough with my calculation. But if I don't find that external force, that means really I have a problem somewhere in the setup of the problem or something, okay? Now, energy is conserved also, all the processes that don't involve kinetic, that don't involve friction or engines. So the total energy, namely the mechanical energy, which is the sum of the kinetic energy plus potential energy, is always the same before and after. Then we have the definition of collisions. There are two types of collisions. There is a so-called elastic collisions where the kinetic energy is conserved, and there is the non-elastic collisions or inelastic collisions where the kinetic energy are not conserved. As a matter of fact, we're usually interested in the ideal inelastic collision where two objects stick to one another and become fused basically with one another. More realistic cases when they don't do either, okay? And that is a region between purely inelastic and purely elastic collision. So that's basically what we'll be exploring in this lab, more or less, okay? So, again, do not forget about the objective. You're supposed to have the objective. It needs 2 or more sentences explaining exactly what you're supposed to be doing in this lab. So that's still there. But it's a good idea, at least for our case in here, for the labs that we do in class, to defer the objective for later. In a real experiment, this will be always the starting point because you can't start working if you don't know what you're going to be doing. So in practice, in real experimental scientists, you start always with the hypothesis and what you want to achieve first before you start experimenting and testing left and right and having no clue into what you want to do. That is not good planning strategy. That's not a winning strategy. In real life, you start with the objective always. But in our labs, because there's a lot of activities and we really have some specific things that we have in mind, so you're allowed, since you're on your own, to basically put the objective at the end, okay? Even if you start with it, even if you put an objective, And while you're doing an activity and things like that, you discover, oops, this is something important. It looks like something I've been doing all along. So maybe I should go back and fix that objective to include this activity in that. This is something that I've been planning to do anyway. I'm doing anyway. And something that you thought probably we were going to be doing based on what you read in the previous stuff, it turns out to be wrong. We're not doing that at all. So you might want to remove it or edit it whichever way you want to. So that's why, since you have a full control over this thing, it's a good idea to defer it for later. Then you have a clear understanding of exactly what you're doing. Come back in here and put it succinctly, put it nicely, exactly what is it that's supposed to be. You need, again, 2 sentences or more, okay? But it should be really descriptive of what you're doing. I'm going to be picky from now on in terms of these 2 things, namely the objective and the conclusion and their structure, okay? So here is question 1. Again, it's structured with multiple questions. I think this one has 24 questions. It's a lot of questions in this one, and more questions than anything else. So it's telling you in question 1 through 6, all of these questions, we calculate the collisions of a 4-kilogram ball and a 2-kilogram ball. Is it 2? No, that's not correct. Let's fix that quickly, okay? Can you guys fix that from your end too? It's a 1-kilogram ball. It should not really matter for this one, honestly, because so this is what we need to fix, okay? It's a 1-kilogram ball. But ignore this statement because the question in the bottom there should really be self-contained in here, okay? So you can read them by themselves, okay? Did everybody catch this thing in here? So it's not a 2-kilogram, it's a 4-kilogram and 1-kilogram. That's what you get when you work very late on things and trying to fix them and trying to edit them and things like that. Thank you, V. So those are the collisions. There is no 2 kilograms whatsoever in this thing in here, at least the first 6 questions. So let's continue with the sharing. I'm gonna repost this thing in here today, okay? I'm going to repost I'm going to delete the old file and put this one in there. So if you already started working on this one, hopefully you have caught this mistake. If not, this is it, okay? But this statement, like I said, has no relevance whatsoever for the questions that come in. So you should not really have had an issue with it anyway. So what is the speed of a 4-kilogram ball with a momentum of 12 kilogram meter per second? Can anybody tell me what the number might be? We have the momentum. Remember the definition of the momentum up there. Momentum is mass times velocity. Mass times velocity. We're given the momentum to be 12. Oh man, why is this thing is flashing? 12. And the mass is 4. And we're asked for the velocity. Did anybody find what the velocity might be in here for question 1? I need help. Does everybody agree with Samantha, Amanda, and V? Amanda and V, you have a big problem if you submit it that way. You know what that is? Okay, very good. Okay, yeah, the units. Okay, the units matter. You lose points in there. So it's 3 meters per second. That's the answer to the first question. And again, you can show the work in here because the mass is 4 kilogram. Okay. The momentum is 12 kilogram meter per second. Divide 12 by 4, you should find the answer to be 3 meters per second. So the velocity or the speed is 3 meters per second. That's the correct answer to question number 1. Question number 2. If the 4 kilogram ball with a momentum of 12 kilogram meter per second, that same ball, collides with a stationary 1 kilogram ball. So that's what I was talking about in the beginning. It's a 1 kilogram ball, elastically, okay, and continues in the same direction. So it hit it and moves in the same direction. So here you have a 4 kilogram ball and a 1 kilogram ball. The 1 kilogram ball is sitting by minding its own business, and the 4 kilogram ball come rolling with 3 meters per second, hits it and continue in the same direction. Okay. And it continues not with 12 because part of its momentum is gone toward the 1 kilogram ball. It continues only with 7.2 kilogram meter per second. How fast will it move? This is similar to the first question. Basically, now it collided with the 1 kilogram, but now it's moving with the momentum of 7.2 kilogram meter per second. Its mass did not change. Its mass is still 4 kilogram. So how much its velocity now after the collision will be? Can anybody tell me?
Will it be like a quarter of that, of the 7 point? I forgot.
7.2. 7.2.
2. So would it be like a quarter from that? Like it just takes a quarter off from that. So if we divide 7.2 by 4 and get the answer?
It should be 1.8 meter per second. Is that correct? Or something
I didn't
like
do the
that?
calculations.
Yeah, Amanda found it and Samantha also found it. 1.8 meter per second. That's the correct answer. So basically it slowed down. It was moving 3 meters per second. Now it's moving less because part of its momentum is gone to the 1 kilogram. Okay, so it lost some of that momentum, which brings me to the ball of the 1 kilogram. That's the question 3. How fast that will be moving? First, we need to figure out how much momentum it received. Remember, the initial ball, the 4 kilogram, had 12 kilogram meter per second. Now it's only moving with 7.2 kilogram meter per second. So the first thing I need to know is how much did the 1 kilogram take in terms of momentum? And that would be $4.8 what, Amanda? You're right. I mean, number-wise is correct, but you still are off in terms of not velocity. This is a momentum. The question is about. Oh, I'm sorry. That's correct. You already found the correct answer at the end. It's the momentum first. My question was it's 4.8 kilogram meter per second, and then you divide it by 1 kilogram, which means the kilogram cancels. So the final answer is correct. Okay. But my initial question was how, because we started with 12 kilogram meter per second for the entire 4 kilogram. The other one was not moving. So the second one has a 0 momentum. So the total initial momentum was 12 kilogram meter per second. The final momentum also must be 12 kilogram meter per second. Somehow, the big one ended up with only 7.2 kilogram meter per second, moving at 1.8 meter per second. Then the smaller one, the 1 kilogram, must have taken the difference between 12 and 7.2, which is 4.8 kilogram meter per second. That's the momentum of the smaller ball. Like Amanda has done, divided by the 1 kilogram to end up with 4.8 meter per second. So you see how fast this thing is in terms of velocities. Let's look at the velocity. Forget everything else. The first one came with 3 meters per second. Now it slowed down to 1.8 meters per second and continued moving in the other one. The smaller one, which was sitting still, now is zooming at 4.8 meters per second. Do you see the difference now? It's moving super fast. Faster than even the first one that started, okay? So that's what I want you to pay attention to for this details in here for questions 1 through 3 so far. Explain why the sum of the 4 kilogram ball and the 1 kilogram ball after the collision, namely the 1.8 meter for the 4 kilogram, 1.8 meter per second. That's what you guys found. Okay? That's what Samantha and everybody else also found, that the initial speed of the after the collision is 1.8. Okay? Samantha and Amanda. and the small ball is moving at 4.8. If I add the two numbers, they should be what? 5.6? No, actually more. 6.6 meter per second, okay? But before that, I only had the 3 meter per second. The other one was stationary. So there is a difference between the initial velocities and the final velocities. Okay? So why do we have a difference, do you think? Or does it matter at all? Can you guys tell me? So when I add the initial velocities,
Is it to get the total energy?
no, we're talking about speeds in here, velocities only. So the initial speeds were 3 meters per second. I'm not sure exactly if I understand you, Amanda, but probably you're right on the right track. So initial speeds are 3 meters per second for the big ball. Okay. At the end, the big and the small are moving with a combined speeds of 6.6 meters per second. The speed is more than doubled. Okay. Is there a problem in here? That's my question. Is there something that is wrong in here? Or everything is well? Can you elaborate, Amanda, on what you said? Added masses? First of all, let's ask a question. Is there an issue in here? Do you guys see that? That initially I only had 3 meters per second. And now somehow the combined, the 1 kilogram and the 4 kilogram are moving with 6.6 meter per second combined speeds. The 4 kilogram is moving with 1.8 meter per second, and the 1 kilogram is moving with a 4.8 meter per second. What do you guys think? Jeffrey, if you said something, I couldn't.
Okay, so the small. I honestly don't. I lost my train of thought, but we're just trying to find the mass or like the combined mass. I'm not really following.
No. Okay.
Because she said added mass, and that's the part.
Yeah, she said added mass, and I was hoping that she could elaborate on that because that's probably where the secret might be. And she put it in question mark. So Amanda, if you're listening, please let me know what you're thinking. Okay. So initially I had a 3 meter per second. At the end, I ended up with a 6.6 meter per second. And that's the question, really. It asks you to add the final speeds, and you find them to be 6.6 meter per second. Compare those to the initial speeds, which were only 3 meter per second.
Sorry, my mic wasn't working. So basically, though, like an elastic collision, when the like object A is more bigger than the object B, isn't it twice the velocity?
Okay.
When they collide?
You probably are right in terms of the numbers, but the thing with it in here, why we have such a difference between the speeds before and after? The question is, does it really matter?
That there's a difference? No.
Yeah.
As long as it's not lost, because.
As long as what is not lost?
Well, the momentum can't be lost, but we're talking about velocity.
So the momentum, since the momentum is conserved, and the energy, we cannot end up with more energy than we started with. If we have the same energy than we started with, we're in good shape. If we have less, then we can explain it that it's fine. Then all is well. We don't care about velocities. Do you guys understand the answer? Thank you, Amanda, for helping me.
Yes.
Okay. So basically, if the momentum, since the momentum is 12, 12, before it was 12, after it was 12. That's basically what we did. If you don't believe me, multiply 4.8 by 1 and add to it 1.8 times 4. It should add up to 12. So the momenta are the same before and after. So we don't really have a problem in terms of momentum. So the momentum is conserved. The issue in terms of the energy, if we do the calculation, honestly, we're going to get to it actually, the energy too, we should not have a problem. So we don't care about the velocities themselves. That's an irrelevant issue. Do you guys understand? So the fact that we have a difference before and after doesn't matter. You guys understand the answer to the question? You know how to answer it now, how to phrase it? It's up to you now. But that's the answer to it.
Yeah, because
Okay.
the question's basically just asking why they're not the same.
Yes, okay.
And obviously they wouldn't be. Okay, yeah. We just explain why.
They may or may not, depending on the masses, okay? But that's an irrelevant, okay? Whether the same or not, it's not an issue at all. What is an issue, though, is the momentum. Okay? Very good. So let's move on. Thank you, V. Thank you, everybody else. So let's move on. Now, verify that this number is equal to 18. So basically, initially, I have a 4-kilogram ball, and we found the velocity from question, whatever, that's to be 3 meters per second. Okay, here. This question 1, we found it 3. So what we need to do, we need to do 1/2 times 4 times 3 squared and check that it's indeed 18 joules, okay? So I need you to check that it is an 18 joule. That's one thing, the energy. And we want to check the same thing for the final. Remember, M1 is 4, V1 final is actually 1.8. When you square it, it's going to be another number. And this one is 4 times 1/2. Now the other mass is, again, 1/2 times 1, because the mass is 1, times the speed. This number is not there. I don't know what this number has to do with anything, okay? Again, we have to fix this thing in here. So I'm going to edit it again. Let me edit this thing in here while you guys are in here. Hopefully we can upload it today. You're doing things on a hurry.
I have a question.
Yeah, hold on. Okay, go ahead.
So since you're editing all these things, should we just like wait on answering the question so we can fill out the
No.
correct one, or?
No, you can, yeah, you can wait. Don't fill this one if you like, but as long as the answer is correct, hopefully you picked up the that there is no such a thing, a 2 in there, okay? I don't know where the 2, sometimes you're typing and you end up
I didn't
with
know
something.
if you wanted us to put it on like the correct paper though, like.
It's fine. Fine.
Okay.
Okay, even if you skip this this form altogether and come up with a new, basically your own filled form, that's fine. Okay.
Okay, just as long as we have the correct answers.
Yeah, as long as you refer to question 1, question 2, and you have all of the syntax that is needed, that's fine. Okay. So that's basically for the second velocity. Remember, was what did we find? 4.8 squared. And if I do the math in here, I should find also 18. So that that answers the question that is previously question 4 in terms of why the difference between them. As long as these two things are fine, we're fine. So that means we really have an elastic collision now, that since these two energies are the same. The kinetic energy before and the kinetic energy after are the same, correct? So we're in good shape. Any question about how to go about these questions, 5 and 6 and all of these questions? Yes? Good? Inelastic collision now. So this is the problem now, the question that we have in here. This is a diesel locomotive coasting at 10 kilometers per hour, has an inelastic collision with a stationary flat car. So the car was not moving, okay? The locomotive, this one, weighs 4 times as much as this car, okay? How fast does the locomotive combination move when it strikes the other one? So here is the deal. Use just the conservation of momentum. Let's call the mass of the mass of the car. What do we call it? Any symbol? Preference symbol?
A.
A? What
Yeah,
did you
like
say?
object A and B.
A, okay. How much would the locomotive's mass will be then?
2.5.
No, hold on.
4A. Did it say
Yeah,
it twice?
40,
Or
40, right?
4A, okay. So this is A, this is 4A, correct? I think somebody's ahead of us already. Somebody's doing, he already found probably the answer. Okay, so this one initially has 4A times 10 must be equal to, when it's an elastic collision, they fuse. The two masses become together. How much mass do I have now when I add the two, the locomotive plus the car? How much total mass do I have now?
50?
50 or 5? 5A.
Well, 5A.
Because
Well,
remember,
because you have A and then which is coasting at 10 kilometers per hour.
so it's 4A times 10. That's the momentum before.
Mm-hmm.
Now 5A times the new velocity, which I don't know what it is. Okay, must be equal. The two momenta must be equal. Conservation of momentum. Now it doesn't matter what the mass of the car is, so we can cancel it. So 40 equals to 5 velocity. That means the velocity will drop to a new velocity. Instead of being 10 kilometers per hour, it's going to be 40 over 5. What is 40 over 5?
8.
So the correct answer should be 8 kilometers per hour. So after the car, okay, you have the wrong units, V. Okay, what is the correct unit then? Okay, very good. So it's the initial velocity was in kilometers per hour. We didn't convert anything. So I have to leave it. The answer is going to be in kilometers per hour too. So you have a locomotive moving at 10 kilometers per hour, which is roughly about what? About 7 miles per hour, okay? And there is a stationary quarter mass flat car sitting by itself on the track. It hits it, now they fuse, okay? They become one. So instead of continuing with 10, it's going to continue only with 8 kilometers per hour. I was going to ask another question to find the kinetic energy after and the kinetic energy before, and we will find the difference now. They're not going to be the same, okay? And the difference will be actually will be less. The difference will go into those velcros or whatever system that, of course, they don't use velcros, they use those things that grab one another and they hold to the cars together. Okay, so whatever energy needed to grab now the car from moving. Okay, so there is a difference in here. So I skipped that part for this one in here because it involves a little bit more calculation that I think you got the point. If you do the calculation of the energy versus if you do it in here, this will be the same before and after. This will not be the same. Case in point, if the two masses were the same, it's going to drop by half and you can do the calculation there. Or if they were moving in opposite direction with the same speed and they have the same masses, they will stick and they will stop. So initially, for sure, you had a big kinetic energy. At the end, you have nothing. So I didn't bother with that part in here. So hopefully you guys have an understanding of how this thing says. Let's get started with the lab. Any questions about these questions from 1 to 7? No? No questions? Everybody is good? Okay, good. So nobody is doubting them. Only one person says no. I hope that everybody. Here is a link for this lab, okay? I'm going to click, and hopefully you guys click on the link also. And we'll meet you from the other end where this thing is. Okay. I'm gonna move what these things are. Okay, I don't know what those things is. Okay. Let me go to the FET activity. So I'm gonna stop sharing that screen now and share with you the link because I really want you to go through the steps of doing this. Every time I give you a link like this one, try not to do the the flash, okay? Try to go to here, Collision Lab 5, HTML5. That's what we're doing in here, okay? Is everybody looking at the activity first? I'm not sure if I'm sharing the right screen or not. Okay, very good. So I'm going to click on it. And when it opens, I'm going to explore 1D. That is where I'm supposed to be. Okay. When you click on it, it brings it up first. And then when you click on it one more time, it brings it to the screen that looks like this. Okay. It's a good idea to turn on the momentum diagram to see what's going on. And to turn on also the momentum vector. Okay. So those are the two things we're going to start with. And it starts with an elasticity that is, elasticity that is 0, I think. We're going to go through the instructions. Let me stop this one. But this is where you control the elasticity. This is completely inelastic. Make sure the reflecting borders are turned on. Okay. And that's it for right now, basically all we need. The masses now, the green one is 0.5. And the red one is 1.5. It's 3 times as much massive, the red one versus the green one. I don't know, it looks like teal to me, not exactly green. But depending on how you look at it, and this one looks pinkish to me more than red. Anyway, so let's go back into the instructions. So when you visit the link, choose HTML5. Do not open the Flash version after the collision, because some browsers, I mean, they don't even allow you to do that. You have to go through so many things to open the Flash, because Flash is basically being demoted completely. So you're going to open Explore 1D activity. Then after that, we're going to start with an inelastic collision. That means the elasticity is 0. Okay. And make sure the momentum diagram is expanded as I expanded it. And the reflecting borders are on, the vectors are on, and for both velocity and momentum. Okay. Which ball has the greater velocity? You can go back into the screen and look at it and tell me which one has the greater velocity, which one has the greater green. If you're confused about that, just remove one of them. Let me stop sharing that screen and go back into the if you're confused because there are so many arrows, remove the momentum momentarily to see which of these two lines is bigger. Okay, which one has a higher velocity? Is it the green one or is it the red one? You should be able to tell from the size of these velocities. Okay, if you want to check the momentum, again, remove the velocity to check the momentum by itself. Okay, which one has the bigger momentum? Which one has the bigger velocity? So those are the two questions that we're going to be asking in here. Let me go back into the instructions. So which ball has the greater velocity? From your observations, you should be you can easily tell. Which one has a greater momentum? From your observations, you can clearly tell. You don't do any changes. You don't give it more velocity or anything like that. By the way, if in case something went wrong, let me go back in here. If something went wrong, you can do one of two things. Either reset it in here. Right now, you don't need to reset. Let's play them. And if I reset, it's going to bring me to where I started from with everything the way it is. If completely you need to go start all over because you put so many numbers in and you don't remember exactly where you were, you can always come back in here. In either case, you have to go back and show the diagram in here, make sure the elasticity is back to 0, turn on the momentum, and you're back to where the instructions told you to start with. So if I do that again, everything is reset, turn on the momentum, make sure the elasticity is back to 0, open the diagram, and in here I was not asked to check anything, okay? So let's go back into the instructions. Explain why the green ball has more momentum but less velocity. So it already answered the questions for you 9 and 8 in here. Hint, what is the definition of momentum in here? So although one of them has bigger momentum than the other one, bigger velocity than the other one, it has actually less momentum than the other. So that has to do with how much mass you really have in here, okay? So it's not just the velocity that makes the momentum. It's actually velocity times mass that makes the momentum. So it's a combination of both. Okay, push play and let the balls collide. After they collide and you see the vectors change, click pause, click rewind, and watch the momenta box during the collision. Watch it more than once, and then do play and zoom, play and zoom, play and pause. I'm sorry, zoom into it, and until basically you know exactly. So what's going on? So let's stop this and let's do exactly what it says to do. Okay. So I'm gonna start playing here. This is what we're supposed to do. We're supposed to zoom on the screen. That's where the zoom they're talking about in here. This is the total momentum. This is the momentum of the particle 2, and this is the momentum of particle 1. Okay. I'm going to pause immediately after they collide. So I'm going to start the collision, the motion, and now pause it. Okay, after the collision. So again, this is my observation. Reset. Okay, make sure that this thing, nothing changed in here. Start and pause and document my observation, okay, in terms of momentum. For example, the total momentum, let's reset it. Did it change from before and after? Looks like it did not, number one. How about the momentum of the first particle? It was pointing in one direction. Did it stay in that direction with the same magnitude? It looks like it reversed direction, and now it's smaller in magnitude. How about the momentum for the big particle? Did it reverse direction or keep its direction? Did it keep its magnitude or its magnitude increased? Let's check it in here, okay? It looks like it kept its direction, but its magnitude became smaller. The total momentum did not change, okay? So those are some of the observations I could document in that equation, okay? After I do this one several times. In all the steps, make sure none of this changes, okay? So, any questions so far? Everything looks straightforward, doesn't it? So what happened to the momentum of the red ball after the collision? So now we're talking just about the red ball, okay? And then how about the green ball after the collision? How about the both green? That's the total of them. So now that's all of your questions, 13 all the way to 14. Which ball has a greater momentum now? Okay, after the collision. I'm sorry, that's nothing to do with it. Change the mass of the ball to match that of the green ball. Let's stop that. Go back into the thing in here. So which mass we have to change? We're changing the red ball so that it matches the green ball. So the red ball, we want to make it exactly matching the other one. Now, which one has more momentum? You can see it from this diagram. And it's clearly now mass 1, okay? Because it has more velocity now. Albeit now this is they both have the same masses. So that should be easy. A lot of these questions you should not really have difficulty with it. And if you do, please let me know, okay? So how much was the total, has the total momentum changed? Do we have now more momentum or less momentum than when we started with? Overall, okay? So let me go back into the screen in here. Remember, look at this screen in here. Look at this total momentum and which way it's pointing and its magnitude. I'm gonna go back to where this was. Okay, no, I can't. It's resetting that thing. So I'm gonna go back to 1.5, roughly. Okay, so this is the direction of the total momentum. It was pointing in one direction. It has a certain magnitude. Now, look at its value in here. It's shrinking. Now, it looks like it has the same magnitude, but the direction has changed, okay? Again, that you may disagree with me, okay? So it's up to you. Now, make a prediction. What will happen if you actually let go of the two balls, okay? And run the simulation and tell me what happens, okay? what happens to the momentum of the red ball after the collision? Now, both of them have the same mass. They're moving now with different velocities. When they move, now they're going to move in one way or the other. So what happened to the momentum? Now monitor the momenta for the red ball, the green ball, and the total momentum, okay? Any questions so far? Looks like it's straightforward. The last part in here, we're going to go back in here and we're going to turn on the elasticity to 100%, okay? And let's go back into the question to make sure I know what the question was asking. Now change the elasticity to predict the motion of the balls after the collision, okay? So now they're not gonna stick, okay? They're going to bounce off. Okay. So basically, let me reset this thing in here. So that's basically, so, but the velocities, there is an exchange of velocities in here, okay? What is the, make a prediction and do the actual experiment. And the same thing for the red ball, and the same thing for the green ball, and the same thing for the total one. Now, when you collect data, you're going to change the elasticity from 100 by decrements of 25 all the way to 0, from completely an elastic event to a completely inelastic event. And you're going to change the elasticity by a decrements of, now, put any random number of masses. I don't want to see them both the same, honestly, okay? So put any number, okay? So that you have the mass in here, you have the mass in there, both masses are entered. And now, what is it? For this one, this is what you got to do, okay? Probably will explain a little bit more on this, okay? So I'm gonna change the masses a little bit, doesn't matter, okay? I'm gonna turn on more data, okay? And I need to report these numbers, okay? So let's go back into the table in here, stop sharing the screen and go back in here. I will need the mass of the red ball. I would need the mass of the green ball. I would need the momentum of the red and the green ball before the collision and after the collision, and whether or not the total momentum changed or not. So let's do that. Let's stop sharing the screen. Let's go back into my activity in here. Make sure the elasticity is sitting at 100. Now the mass, let's put a rounded number in here. I don't like this one in here. Let's put it 0.9, okay, 0.90, enter. So when you click on these numbers, you can enter them manually, okay? So mass of the green ball is 0.7, mass kilogram. Mass of the red ball is 0.9 kilogram, okay? We don't care about the positions. We don't care about the velocities. We care about the sum of these two numbers. What is negative 0.35 plus 0.9? The answer should be 0.6, no, 0.55, is it? 0.55? Now the sign matters, okay? The sign matters, okay? So it's a positive number in this case, okay? It's a positive number that I'm going to put 0.55, okay? Let me stop sharing the screen, make sure that I am in the right place in there first. I'm sorry, we should really reset first. Okay. Okay. This is what I was talking about. Reset the whole thing, okay? Start all over. Make some random mass. I said 0.7. Let's make it 0.7 in here. 0.7. Enter. And this one is 0.9. Enter. And more data. Fine. And the elasticity is there. Show the momentum is fine. We don't care about these vectors. Honestly, we care about the numbers now. Okay, for this part. Okay. So the numbers I gave earlier were not correct. So this is actually we need to start from the beginning, okay? When you're doing this one, always between every question, make sure that you have a starting point in here, okay? So the elasticity is sitting at 100. The masses, I chose them, in my case, 0.7. You don't have to do 0.7. I chose the second one, 0.9. You don't have to do them 0.9, as long as there are some random numbers in there that you can manage. We don't care about the positions. We don't care about the velocities at this point. We take just whatever values they're given to us in this case, okay? Now, 0.7 plus negative 0.49, negative 0.45. If I add the numbers, it's going to be 5 minus 2. It's going to be a positive 0.25. So the momentum is positive 0.25. If you like to see the diagram, it's fine. You can see the diagram. Let's start the collision. And immediately after the crash, we're going to stop it and watch these numbers in here, okay? So we're going to start the collision. Now its collision is over. Now the numbers are negative 0.48 and negative 0.73. I need to add them. Remember, these are algebraic sums. That means negative 0.48 plus 0.73. When you add them together, you're actually doing a difference. So in this case, it's going to be 5.25 again, okay? So when I stop in here, come to my lab experiments in here, to my lab report form in here. I chose this one to be 0.9. I chose this one to be 0.7. The velocity, the momentum before was 0.25 kilogram meter per second. This one was 0.9, 0.7 kilogram. This one was 0.9 kilogram. And the momentum after turned out to be the same thing, 0.25 kilogram. So I come in here and check yes. Okay, let me remove the commenting tool in here. We go back into stuff that I can. So I put yes in here, okay? So was there any change in momentum? No. Change in momentum during the yes or no? No change, okay? The momentum stays the same, okay? So the answer should be no in this case. There was no change in momentum because this momentum was 0.25 kilogram meter per second. This one also, that's my simulation, okay? It's not yours, okay? Yours may be different, okay? Kilogram meter per second, okay? Now, the main thing in here is to lower, let me stop sharing the screen, and let me go back into this one in here. I'm going to first reset this, okay? I'm going to change the elasticity now down to 75. Okay. Note the momentum before. Do the collision. Stop it. Note the momentum after. Add the numbers and check. Was there a change in the momentum before and after? If there is, I'll check yes. If there is not, I check no. Okay? And continue with the table until I finish all of the data. Again, your numbers might be completely different than my numbers, which is fine. But at the end of the day, what matters is the last column. Okay? There should not be a single yes. There should be always no change, no change, no change, no change, no change. Okay? This is really the heart of the experiment in terms of what we're doing, okay? There should be no, 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 and no. That's what we expect to find anyway, okay? Then based on the observation of what happened to the momentum before and after the collision, your conclusion in here, unless something went completely south or you had difficulty big time with your problem, with your lab experiment, you could end up with a yes somewhere, which you need to explain, okay? No, there was no change in momentum, everything looks good. And the conclusion here needs to type into the objective and make sure if you have any data to report or observations based on the numbers that you have in there to report them in there. Any questions about the lab?
Yeah. Are you gonna? I don't know how to edit out the mistakes that were made like earlier.
Okay.
Are you gonna?
You want it now?
I'm just asking.
Okay. Hold on. Okay. Give me a second in here. Let me edit the lab report form. Since you guys are in here, I want to make sure that it's working too. So I'm going to go in here and let me first of all save my file. Let me first close it without saving it, because if I do save it, it's going to save all of the stuff that I have in there, which is not really what I want to see. Okay, just want to edit it one more time without anything in it. So to fix, what was the error? First error was we needed to fix. There was no 2 kilogram in it. Questions 1 through 6. Well, that looks like it saved it, at least now. How about the second one for the kinetic energy? No, that did not change it. Okay, let me tools, edit. Let me fix that. Okay. Let me make sure that the other. Okay, so there was only one thing I had to do now, save. So I'm gonna come in here and link document, upload document. I really should have given it a different name, because now on Canvas I will have 2 files, both of them with the same name, and I wouldn't remember later on which one to delete, because there will be 2 files, albeit both of them are compliant in terms of Canvas requirements for accessibility. So there should not be a problem in that. Lab04, lab report form. Oh, did you notice that there is a file name that is completely nonsense? It's misspelled. It's not momentum, it's moyementum. Did you guys notice that the file when you downloaded it? Or you took it? Did you say notice the file name? Do I need to fix the file name too? Let me change the file name, okay, because right now, so I know which one to delete now, the one that is misspelled. Rename. It's not momentum. So it's momentum, okay? So now it has a correct name. Let me go back in here, upload, fall, physics 11, labs, lab 4, and now it's correct name, spelling too. And let me edit it, lab 4. Did anybody notice the spelling of the file, that it was misspelled big time? Save. Can you download the correct file now, everybody? Was it Taryn who asked that question earlier also? Taryn? Yes, okay. So let's download the file, please. It should have fixed the 2. One of them is the formula. It has an extra 2, which is really nonsense. And the other one has the statement about that has some thing in there. Okay. How does it look, Taryn?
The mass is fixed, and so is the title in the file.
Okay, thank you. The file name was completely nonsense. Okay. Okay, Amanda had it working, so we're waiting for Taryn. Okay. If you guys don't have any questions, then we're going to stop the recording. And again, I'm going to leave the session open if in case you guys choose to stay here.
I think someone asked what the lab discussion was for this week.
Oh, the lab question for this week. Hold on. Let me go back into the things. That's a good question. Oh man, I didn't even open. I closed it. Hold on. The lab question that I was having in mind that I did not ask, and I was hoping that you guys will work on it, is question 7. Basically, we calculated the momentum before and the momentum after, and that's how we found the velocity of the car and the velocity of the locomotive, basically car, when they stick together. Is that, would we expect the energy, the kinetic energy, to be the same or not? The answer, of course, should be no. Okay, because this is an inelastic collision. Okay. Does this make sense? And like the previous one, which was elastic, which we found them, both of them, to be 18 joules. Does this make sense to you guys? I need confirmation. Okay, Jeffrey. Very good, Vanessa. Okay, guys, we're going to stop the recording now. And the session will be open until 9 p.m. unless everybody leaves or most of you leave. Then in this case, probably, if you have any question, please let me know. This is, I don't think that should be any problem. Don't forget, you have those who did not submit the lab that you should do tomorrow by 11 p.m. And this lab is due again a week from today plus 1 day. So it's going to be due Friday also at 11 p.m. Okay, so I'm going to stop the recording right now.
1 second, Professor. What was the discussion answer? You know how you post, was it the question 7 that you were explaining?
Question 7 basically was, we used the conservation of momentum to find the velocity of the locomotive flat car together. The question is, we did not calculate actually the energies, but had we calculated them, we would not expect them to be the same because this is an inelastic collision. The kinetic energy before should be more than the kinetic energy after because they fused. Okay?
Okay, but is that the answer to our discussion?
Yes, we always discuss
Then,
the question.
you know how you post a discussion and then we have to.
Yes, okay, so let me put the question in here since you guys are here. So the question is, the momentum helped us find the conservation of momentum, not the momentum, conservation of momentum. We have to be accurate, okay? Conservation of momentum helped us find the combined velocity, and we did not, and the kinetic energy after should be less than the initial, although we did not calculate it. That's a point in here, but you could calculate it. Of course, you need to know the mass of the car. That's why we, if you really want a number, okay, the initial should be less than the initial kinetic energy. Okay, kinetic. Watch my spelling, okay? Sometimes I'm saying something, I'm spelling some nonsense stuff. Kinetic, the initial kinetic energy, because the collision is inelastic. Okay? You can download this discussion thing. I think we did last one too.
The last lab? Yeah, it was to answer the survey.
Yes, yes. It's about the survey. Thank you. It's going to go back into my notes in here. It's about the survey that you're going. You should have received it by now, okay? Please fill it out at the best of your abilities. Okay? Hopefully you're challenged enough in this class that you're working. You're not sleeping in this class. Are you? Should we do more stuff than what we're doing now? Okay, very good. Thank you, Sharon. Okay, guys. Like I said, I'm going to stop the recording. Okay? And I'm going to leave